Hello everyone. Uh, we are studying the concurrency portion of our operating system course, and we had studied what are threads, how we can write multi-threaded programs, and what problems arise when we access shared global data through multiple threads within a single program. Okay, they can corrupt each other's values. Therefore, we have to implement some kind of synchronizations so that the multiple threads of a single program access or modify the shared data in a mutually exclusive fashion. Okay, so in the last chapter, we have studied about locks, how locks help us implement mutual exclusion within multi-threaded programs. Okay, so that our threads access shared global data only one at a time. They enter their critical sections one at a time and modify the shared global data one at a time. Okay? So locks can be used to implement mutual exclusion in our multi-threaded programs to ensure correct behavior so that multiple threads do not corrupt or modify each other's data. In this chapter, which is the chapter 29 of your book, we'll continue the same thread and we'll see some examples of locks in data structures. How do we use locks inside data structures when we have global data structures shared between multiple threads? Okay? And multiple threads are trying to modify these shared global threads, shared global data structures concurrently. So let's see some examples. So we'll again start by a simple example, and currently the data structure that is shared between multiple threads is this simple structure, counter underscore t, and it has only one variable of type integer whose name is value. So there's an init function which will initialize this structure, the value inside this structure. And then we have two functions, one called increment and the other called decrement, which will respectively increment or decrement the value of this structure. Okay? And then we have another function which can return us the current value of the structure and we can display it. So these increment and decrement functions, let's assume that there are multiple threads running within this program which are sharing this global data structure. And within those multiple threads, we are calling this increment and decrement functions on this global structure concurrently. Okay, there could be many threads running on a single core or on a multi-core processor, and they are all accessing this shared global structure and increment and decrementing its value. So what can possibly go wrong, or is this code correct? Will it work correctly, or is it thread safe? What does the term thread safe mean? Thread safe means that your code is written in such a way that it is safe for multiple threads to run this code concurrently, okay, either on a single core processor or on multi-core processors. So if this if this code is run in multiple threads concurrently, the increment decrement functions are being called multiple times concurrently in multiple threads. So will this code work correctly? Okay. If it works correctly, then we say it's a thread safe code. And if it doesn't work correctly, then we'll say it's not a thread safe code. Okay. So that's the definition of thread safe, that the code can be run in multiple threads concurrently without any fear of being incorrect, okay, without any fear of race conditions or indeterminate behavior. So is this code thread safe? Assuming a main thread, this global variable is declared, main thread initializes this structure, and then multiple threads increment and decrement its value. So pause the video here, give yourself 2-3 minutes and look at the structure of the code and see whether this code is thread safe or not. Your previous chapters should help you in this regard, especially that example with counter is equal to counter plus 0. Okay, so if you have thought about it, then you would know that this code is essentially the same as counter is equal to counter plus 0. Counter is equal to counter plus 1. because in that code we were just incrementing the value, and here we are both incrementing and decrementing the value. So otherwise this code is essentially the same, that multiple threads are sharing a global variable and they are accessing this global variable without any synchronization, and they will be updating this value concurrently, which means multiple threads would enter their critical sections concurrently and update this value. So this will result in corruption of this value, and ultimately we will not see the correct result at the end. So how can we make, so this code is not thread safe. Okay? So how can we make this code thread safe? Again, we'll have to implement mutual exclusion and make sure that only one thread is able to enter critical section and update this value at any given time. So if you are able to implement that kind of mutual exclusion, then we can make this code thread safe. So how do we implement mutual exclusion? Again, the locks that we studied in the last chapter will be used here, and we will associate a lock variable with this global structure, and we'll make sure that only one thread can access this global structure at any given time. Okay, so only one thread will be access it, and only one thread will be able to modify it at any given time. Okay, so multiple threads will not be able to access this structure concurrently. So how do we use these locks? I hope the behavior of locks, you still remember that lock is a variable which exhibits a certain behavior. We can call two types of functions on lock, acquire and release. And when multiple threads try to acquire a lock, only one of them will succeed in acquiring a lock, and all other threads will wait or block until they get the lock. Okay, so only one of them will be successful in getting the lock. So in our initialization function in main thread, we'll initialize this value, the global structure, and we will initialize our lock, which we have associated with this global value. So this is done, and then we'll create multiple threads and run those multiple threads calling increment and decrement all the time. So within the increment and decrement functions, if you guys see, these were our critical sections. Okay, the update of the value, this was our critical section. And if you see, we have used locks the same way that we have studied in the last chapter, that we have defined a protocol inside our critical section that to enter a critical section, a thread must first acquire this particular lock. Okay, this lock, which is part of this variable and has been associated with this value. So every thread, before it enters the critical section and updates the value, will acquire this lock. Once it has acquired the lock, only then it will enter the critical section, update the value, and then after updating the value, it will release the lock. Similar protocol has been followed in decrement. Okay, threads, before decrement value, threads acquire this lock. Only when they have acquired the lock will they enter the critical section, decrement this value, and after decrementing, release the lock. Similarly, for reading also we use the same protocol. So let's say there are multiple threads running and they are calling increment and decrement simultaneously. So all the threads, they will try to, let's assume, call these functions concurrently, and they will access to modify the value at the same time. So what will happen is all these threads, let's say they call increment simultaneously or concurrently, so they will try to acquire this lock concurrently. Okay? And we know from our discussion of locks from the last chapter that the behavior of the locks guarantees that if multiple threads try to access or acquire a lock concurrently or simultaneously, only one of them will succeed and the others will block. Okay, so this pthread mutex underscore lock function, which is trying to acquire the lock, will return for only one of those threads trying to access this lock simultaneously, who will succeed in acquiring the lock. For all others, this lock function will block and it will not return until they have acquired the lock. Okay. So only one of the threads will be able to acquire the lock, and for that thread, this function will return and it will be able to enter its critical section. So that particular thread will update the global variable alone. Okay, and then after updating, it will release a lock. So once it releases the locks, then all other threads that were waiting for this particular thread, one of them will now get this lock. Okay, so the pthread underscore mutex underscore lock function, which was blocked for all these threads, will unblock for one of those threads, and that particular thread will return from this mutex underscore log function and enter its critical value. Okay, so this second critical section. So this second thread will now update this value again. Okay, and then after releasing, it will release the lock after updating the value, and a third thread will get the lock. Okay. And similarly, for if any thread was decrementing and had called this mutex underscore lock function, it will also be blocked until it gets a lock. So we are using, by using locks, we are making sure that only one of the thread is entering the critical section and only one of the thread is accessing the critical this global value at any given instance. Okay. So since the value is being updated by only one thread at a time, so there is no chance of one thread overwriting the value of the other thread. Okay. So we have implemented mutual exclusion, and this code by now, I hope you are able to see that by now this code is thread safe. We can run this code simultaneously, concurrently in as many threads as you want, and it will behave correctly. No thread will overwrite the value of the other thread. So this code is now thread safe because we have implemented mutual exclusion in this code using a lock. Okay? Only one thread will be entering its critical section at any given time. Second question is this code scalable? This code is thread safe, but is this code scalable? So here I will define the term scalability in case some of you have not heard this term. Scalability means if you have more resources, let's say if you have more number of cores on your processor, will your code run faster, or will its performance remain the same, or will its performance degrade? So let's say if you have let's define two dimensions this term scalable. One dimension will say you have a code, you run it on a single core processor, its performance is, let's say, X. You run it on a quad core processor, what's its performance now? You run it on a 100 core processor, what's its performance now? And you run it on 1000 core processor, what's its performance now? Okay. So normally the idea of scalability is that as you put more resources on a problem, as you give more resources to a program, as you give more number of cores to a program, its performance should improve. Okay, so if its performance improves with additional resources, additional hardware cores, then we say this code is scalable. Okay? If this performance remains same, or if it degrades, then we say this code is not scalable. Okay? To give you an example, let's say you have to search an image in a database of images. Now, if you have a single, let's say that database has 1 million images. So if you have a single core processor, then you will have only one thread running, and it will go through all the 1 million images and see if it can find that image in those 1 million images or not. But if you have a quad core processor, then you can basically write a multi-threaded program, and that multi-threaded program will basically divide this database into 4 parts, each of 250,000 images, and it will use the same image in all the threads, in 4 threads, to go through all the 250,000 images. Okay, so now one thread is not going through 1 million images, one thread is only going through 250,000 images. Okay? And all these 4 threads are running in parallel. So ideally, with more resources, number of cores grew from 1 to 4, the execution time of our program would decrease by a factor of 4. Okay. And now if we extend this analogy to a 100 core processor, then again we will write a program with 100 threads, and to each thread we will give 10,000 images from the database, and each thread, instead of going through 1 million images, will only go to 10,000 images, and all these threads will run or execute in parallel, and ideally the runtime of our program would be lowered 100 times, okay, divided by 100. So this program is very much scalable, okay, because the more resources we put in terms of number of cores, etc., the further our execution time of our program reduces. So this is a highly scalable program. So I hope from this example it is clear that what do we mean by scalability, that how does our program perform when we give more resources to it. Another dimension of scalability will be, let's say you have a program that solves a problem. What if you increase the size of the problem, keeping the same hardware? Will the uh, will the execution time of a program execute linearly or exponentially? So if by increasing the size of the problem, the execution time of our program remains the same, or if it increases linearly or sublinearly, then we say that our program is scalable. But if we increase the size of the problem, and the execution time of our program increases exponentially or superlinearly, then we say that our program is not scalable. So it can work on small scale problems, but it does not work on big scale problems. Okay, so keeping these two dimensions of scalability of this definition, one in which for the same multi-threaded program we basically increase the number of resources, and secondly, for a program keeping the hardware same, if we increase the size of the problem, then what's the effect on the uh, execution time of that program. So keeping these two definitions, if I ask you what will be the scalability of this particular program if we run it in multiple threads on a single core processor, on a 4-core processor, or on a 100-core processor, is this program scalable or not? Let's say I have to count from 1 to 10 billion. Okay, so we are calling on the increment function, etc. So if I do this counting in one thread on a single, let's say we have a multi-thread program which can create many threads. If we run it on a single core processor, and if we run it on a 4-core processor, and if we run it on a 1000-core processor, will the execution time decrease accordingly? Will it run 4 times faster on a 4-core processor? Will it run 1000 times faster on 1000-core processor? So the fact that only one thread is able to access the value and increment it, that should give you a hint. Okay, and you can pause the video here, give yourself a couple of minutes and see whether this code is scalable or not. So moving on to the answer, if you see or run this code on multiple cores, you will see that this code is not scalable. Why is this code not scalable? Because even though there are multiple threads running, only one of the threads is doing useful work. Okay, only one of the threads is able to increment the global value. Okay, all the other threads, they are running on multiple processors, but they are just waiting for the lock. Okay, so because of mutual exclusion, only one thread will be able to enter the critical section, and only one thread will be able to access the lock, the global value, and update it. So in this particular example, this counting scheme is not very scalable, because as the number of threads increases, most of the threads, they are just waiting and not doing useful work. Okay? So compared to this multi-thread program, a single thread program will run faster, okay? Because it will be updating the value, and it will have no overhead of multiple threads, context switching, or accessing the logs, etc. So locking can affect the scalability of our programs, okay, because locking becomes a bottleneck in the sense that only one thread is able to access the global value. All the other threads are just waiting for the lock to be available. So how can we make this code scalable? Well, the particular example that we studied is not very scalable, but there are some variations of this example, some modification. If we modify the problem a little, then it becomes very much scalable. For example, if you want to count a value, then there is a concept of approximate counting. Approximate counting says that most of the time, in most of the cases, you do not need the exact value of the counter. If you have a rough idea and approximate value of the counter, that suffices. To give you an example, let's say you have multiple sensors that are uh, installed at the entrance of your hostels. So every time a person passes, the sensor will detect that a person has passed, and it will send a information to your program. Okay? Now your program has multiple threads running. It has multiple threads running, and for each hostel it has a thread, and it is receiving the information from the sensors of each hostel, and it is updating the information how many persons have passed collectively in total through all the gates of all the hostels. Now the administrator has a program which is showing it this global value of all the persons that have passed, and it's a global variable. Now the administrator, if it wants to basically look at this variable at any given instance, the exact number of persons passed may not be important to them. They just want to have a rough idea whether the number of person passed is in tens, is in hundreds, is in thousands. If it is like 5,673, this exact number is not important. The fact that 5,600 something people have passed, this give them a good enough idea of how many people have passed through all the gates in all the hostels. So this is an example where we are doing counting, but the exact value of the counter is not important to us. A rough idea is good enough. Okay, so in this particular case, instead of doing exact counting that we were doing in the last example, we apply this technique of approximate counting. So what approximate counting, the implementation looks like this, that you have a global counter, which will basically calculate the total number of all the people passed, but each CPU or each thread has its own local counter. Okay? So local counter, let's say in this our example, there is a thread per hostel, and the local counter for each thread is keeping track of how many people have passed through that particular hostel's gates until now. Okay? So what happens is all these threads, they basically update their local counters locally. Since these local counters are not shared between other threads, so the access to them does not need to be synchronized, and we do not use locks to access these counters, because local counters are specific to each thread. Okay? They are not shared or modified by other threads, so we do not need locks to access these local counters. So these threads basically access local variables without any locks and keep updating their local counter. And after a certain period, S, they update their information and send it to the global counter or add it to the global counter. Okay? So after a period S, a thread would transfer all the counting that it has done to the global counter, and it would again start from 0. So here let's look at this example. We have like 4 threads running in parallel, and this is the state of the global counter. So every thread has a local counter, L1, L2, L3, L4. So each thread is after some time getting the sensor data and updating its local counter. So you see after some time L3 becomes 1, 2, 3, L4 becomes 1, it remains 1 for some time, and 2, and then becomes 2. L2 remains 0 for a long time, and after some time it becomes 1. Similarly, L1 0 0 1 2 3. It continues incrementing. So after a time period S, each of these threads will transfer its local information to the global information, global counter. So in here S is equal to 5. Okay, so after 5 increments, they will transfer their information to the global counter. So you see here the L1 counter, it reaches 5 first of all. So it will transfer this information to the global counter. So here the global counter, which was 0 during all this time, has now become 5 because it is updated with the information from L1. And L1, after giving all this information to the global counter, it starts from 0 again, okay, to accumulate local information or increment the local variable locally. Similarly, L4, after some time, it will reach 5, and then it will also transfer its information to the global counter and start from 0 again. Similarly, L2 and L3 will do the same when they reach 5. So you see, the counting is being done locally in a distributed fashion. But after some time, this information is transferred to the global variable, and the global variable gets updated. For example, if we see the global variable here, it's 0 all the time. Right? So there's a big difference between the global counter and the actual number of persons that have passed through gates. Okay? For example, here it's like 4, 6, 10, 11. So global counter is 0. However, 11 persons have passed through the gate. So there's a big difference. But after some time, when the global variable is updated, this difference becomes smaller. So the global variable is now 5, and actually there have been like 7 and 8 and 5, 13 people that have passed through these gates. Okay? So the difference between local actual value and the global counter has become smaller. And now here the global counter has become 10, and 16 people have passed through the gates. Okay? So difference has become even smaller. So the difference between the actual number of people passed and the global counter will fluctuate. Sometimes it will be slightly larger, sometimes it will be very close to the actual value. But with time, this difference will decrease, or at least a percentage difference will decrease, and the global counter will give us more or less an accurate view of how many people have passed through all the gates of all the hostels in together. Okay, so this S can be modified according to your needs. Basically, the larger the S, the greater the difference between the value of the global counter and the actual value or the actual number of persons that have been passed. So the key thing here is that our threads, most of the time, they are accessing local variables. Okay? So they do not need to do synchronization to access local variables. Only when they access the global variable, which is shared between all the threads, only then they need to do synchronization, and only then they need to acquire locks. Okay, so the waiting time for each thread would be very small because uh, each thread will not be accessing the global variable all the time. Okay? Each thread will be accessing the global variable after a period S. So for S time, the thread will be working without using the locks, and only after S, for a small period of time, just to transfer its value to a global variable, it will access the locks. So the need to synchronization is not all the time. It has become very, very low compared to our first example. Threads need to synchronize, or threads need to acquire locks only for a small fraction of time. Okay? So only for that fraction of time, the global variable or the synchronization will become a bottleneck. For the rest of the time, these threads are running independently. Okay? They are not waiting all the time as they were doing in the last example. So this is an example which basically implements counting, but in an approximate manner. Now the advantage of this um, scheme is that it is very, very scalable. Okay? As S increases, threads do more work independently, and threads synchronize less and less. So they can work independently in parallel. And if there are more resources available, then the time to execute of this program will reduce, because more of and more work will be done in parallel on multiple processors. So approximate counting is much more scalable than exact counting. There are situations in which approximate counting is enough, good enough. So now let's go to another data structure, which is a linked list. So you must have studied linked list in your data structures course. So linked lists are dynamic data structures in which we use these nodes which contain the value and the next pointer. So it's a singly linked list. So let's assume we have a linked list that is shared between multiple threads, and each of these multiple threads is trying to insert nodes in this linked list and delete nodes from this linked list. Okay? So give yourself a pause here and imagine if we share this or such a linked list between multiple threads concurrently. What can happen if multiple threads try to insert or delete nodes from this linked list simultaneously or concurrently? Give yourself a pause here for 5 minutes or more, and then think about the consequences, what can happen if we share this global linked list between threads without any locks or without any synchronization, and multiple threads try to insert and delete nodes concurrently. Okay, so I hope you gave yourself a pause and thought through what can happen if multiple threads try to insert or delete nodes from a globally shared list concurrently without any synchronization. Okay. So again, as you can imagine, I hope you have reached to the conclusion that things can go bad because multiple threads, they are accessing the same resource, the same linked list, and they might access uh, the same node. Okay, so let's say it's node number X. So one thread is trying to insert a node before or after node number X, and another thread is trying to delete node number X. Okay, so these threads would mess each other up. Okay, because in linked list we are handling multiple pointers simultaneously doing an operation, and those multiple pointers can be overwritten by another thread, and this can mess things up for multiple threads which are trying to access a globally linked list concurrently. Okay? So again, to avoid this situation, we will use synchronization between threads so that only one thread gets to access the linked list at any given time. So to implement this, again, we'll use locks. So this is our structure for linked list node, and this is our structure for linked list. Okay. So in the structure linked list, we have pointer head and a variable lock. So in the init function, we'll initialize our list and we'll initialize our lock. So now we have to implement two functions, list insert and list lookup, or it could be list delete, whatever you want. But we have to implement them in such a way that they are thread safe. They can be called from multiple threads concurrently, and still our program should work correctly. So again, we will basically define a protocol for this accessing this linked list, that every thread, each and any thread that wants to access this linked list should first acquire this lock associated with this list. And once it has acquired this lock, only then it can go ahead and access this linked list. And once it has a lock, it can go ahead, access this linked list. It can insert, delete, whatever it wants to do with that linked list. And after it has done its operation on that list, it will release this lock. Okay? So the same thing is happening in insert function as well as lookup function. Okay? We acquire the lock, then we do our lookup, and then we release the lock. And similarly, if there is a delete function from the linked list, then it would have the same protocol. we would first acquire the lock, then we would access the list, delete our desired element, and then release the lock. So by using a lock, we are ensuring that only one thread is being able to access the linked list and modify its data structures and contents at any given time. Okay? So all other threads that want to modify the linked list or access the linked list at the same time would block, because they will also have go through this protocol. Okay, so when one thread is in its critical section and is accessing the list, no other thread will be able to acquire the lock and access the critical section and modify the list. So once the first thread who is in the critical section has finished its task, it will read the lock. Only then some other thread will be able to acquire the lock and it will access the linked list. So I'm not going into the details of how the linked list works, because this is something that you have already studied in your data structures course. I'm just giving you how we can access this linked list concurrently. Same goes for lookup. So whenever you want to access a linked list, first you have to acquire the lock. And if multiple threads try to access a linked list simultaneously, they all try to acquire the lock simultaneously or concurrently. The behavior of the lock ensures us that only one of those threads will be able to acquire the lock and the others will have to wait. So this is how we can share global linked lists between different threads in a thread safe manner. So this again implementation is thread safe, but is it scalable? If our linked list becomes bigger and bigger, there are more and more threads trying to access the linked list simultaneously. Will the performance improve, or will it get slower? Will it degrade? So again, I hope you guys can see that this problem is the same as the single counting, exact counting problem, that only one thread is being able to access the linked list at any given time. Okay, so when a thread is accessing the linked list, it will acquire the lock, and this lock will basically block access to the whole of the linked list for all the other threads. Okay, so only one thread is doing any useful work, all the other threads will be waiting for the lock to become free. So this implementation again is not very scalable. So it is possible that there are two threads that want to modify this link. This is a very big linked list, and there are two threads that want to modify the linked list, but they don't. They both want to access different parts of the linked list. One thread wants to modify the start of the linked list, and the other thread wants to modify the end of the linked list. So we know that these threads will not be corrupting each other's data because they are not accessing the same part of the linked list. But still, our implementation does not allow this. Our implementation has only one lock associated with this list, and this lock is basically controlling the access to whole of the linked list. Because only one thread will be able to access the linked list, even if we are sure that they are not, they will not be corrupting each other's data. So this implementation is not very scalable. Okay. You can find more scalable or more efficient implementations of linked lists, which, for example, in the example that I cited, which will allow multiple threads to access and modify the linked list if they are sure that they do not corrupt each other's data, because they are accessing different parts of the linked list. Okay. But this is, that particular implementation that we have studied is not very scalable. The other one would be scalable because multiple threads can work in parallel. You can look such implementations on internet. So this implementation is not very scalable. Now let's take another data structure which we call queue. A queue again, what is a queue? How does it work? How it is implemented? You guys, I'm sure, have studied this in your data structures class. So we are not going into details of how a queue is implemented, but we'll see what is the principle of the queue and how a queue can be shared between multiple threads in a thread safe manner. So a queue again, as you guys know, is a data structure which works in a FIFO manner. Okay, so we insert things in a queue from the tail side and remove elements of a queue from the head side. Sorry. So this is a node of a queue which contains a value and an X pointer, and then this is a data structure queue in which we'll have a pointer to the head of the queue and tail of the queue. And since logically the head and tail are separated, and most of the time the linked list's head and tail are different, so multiple threads, they would be operating on different ends of the queue. So here what we can have is that to allow multiple threads or at least two threads to access the queue simultaneously and modify the content of the queue dynamically in concurrently, we can have two locks. One lock which is controlling access to the head side of the queue, which is called a head lock, and another lock which is controlling access to the tail side of the queue, that is called tail lock. Okay, so basically any one thread can access any one queue, one end of the queue. Okay? At any given time, at most two threads can access the queue simultaneously, one from the head side and one from the tail side. Okay? But these head locks and tail locks will ensure that no more than one thread can access the head side simultaneously. No more than one thread can access the head side simultaneously, and also no more than one thread can access the tail side of the queue simultaneously. Okay? So this is our implementation, the data structure, and then inside the initialize function, we'll basically initialize our queue and initialize these two locks. Now here we have, when we initialize a queue, we put a dummy node inside a queue. Okay, this is a malloc. We have allocated a dummy node dynamically, and we have inserted this as part of the queue. Okay, so why is this here? This is a question that I would like you guys to investigate. What's the advantage of keeping a dummy node inside the queue? Okay, this node is not visible to the outside user of the queue, but internally we are using it for our convenience. What is that convenience? Kindly think about it. So these two locks are initialized, and here we have two functions that we are going to perform on the queue. InQueue, which will insert element in the queue from the tail side, and DQueue, which would remove elements from the queue from the head side. So since the InQueue operation is happening on the tail end of the queue, therefore to perform this operation, we will basically access or acquire this tail lock. Okay, so all the threads that want to modify the queue and the tail of the queue will have to access the queue through this tail lock. This is a protocol that we have defined in this InQueue function. So by using this lock, we are ensuring that at any given moment, only one thread is being able to modify the tail end of the queue. Okay, so only one thread will be able to insert an element in the queue at any given time. Other threads will be waiting if they're trying to perform the same operation. Okay, and ultimately they will also get a lock, and then they will perform their operation. Similarly, on the head side, we are basically using the head lock to remove the element from the head side of the queue. Okay? So to do the DQ operation, the protocol is that any thread that wants to do the DQ operation, it should first acquire the head lock first, and then it would go ahead and change and modify the head of the queue, remove element from the head, modify the head, and after updating the head, it will release the lock. Okay? So again, using the head lock, we are making sure that no more than one thread can access the head side of the queue and remove an element from the queue at any given time. Okay? If multiple threads want to remove elements from the queue, the implementation of locks ensure us that only one of them will succeed, and only one of them will be able to access the queue and remove an element from the head. The others will wait and will only be able to enter the critical section on their turn when they have acquired the lock. Okay, so mutual exclusion again is implemented here and ensures us that only one thread enters the critical section at any given time, and therefore the program executes correctly. Okay, and this implementation again is thread safe. Another data structure that is used very much is hash table. Okay. A hash table, you guys know, is a series of buckets in which we could put values. So again, I hope at least that you have studied how a hash table works in the data structures class. So let's say this hash table has 101 buckets. Okay. So each of these buckets is a list. Okay. So there's an array of list. So each element of this array is a list. Okay. The list that we just studied a few slides back. Okay. So each of which basically inside it has a lock. Okay. So each of this is a list that we have studied and has a lock which controls access to each of these lists. Okay, so there are 101 lists. So each list will have a lock inside it. So there are 101 locks in total in this data structure. So when we initialize our hash table, we initialize each of these lists, and if you go and look at the list init function, we'll see that it initializes the head of the list as well as the lock inside the list. All these are initialized in the main section. So now manipulating the hash table, we have these two functions, hash insert and hash lookup. Okay. So hash insert basically gets a new value key, and it inserts this key into one of these buckets. Okay. So it will calculate the bucket for this value, the new value key, and then based on the bucket calculation, it will insert this key value into a particular bucket, into a particular linked list. Okay. So each new value will be inserted in one of these 101 linked lists. So inside this list insert, we've already seen that this list insert function will be following that protocol, and it would be basically inserting this element inside the linked list in a thread safe manner. Similarly, same thing happens for a lookup. You have to look up a key, and so it calculates the bucket for this key, and it does a lookup in that particular bucket for this particular value key. So the buckets are basically linked lists, so the lookup will be performed inside the linked list. Again, we have seen this lookup function in the previous slides, that it follows the same protocol. While accessing a linked list, it will first acquire the lock, then enter its critical section, and then after completing its task, release the lock. Okay. Multiple threads trying to insert or look up in the same linked list will basically access a linked list in a mutually exclusive manner. So here the advantage here is that hash table is an array of lists. Okay, so multiple threads can access this hash table simultaneously, concurrently, and if within the hash table, if they are accessing a different bucket, then all these threads will be able to perform their operation simultaneously, concurrently. Okay, so if all the threads are accessing a different bucket, then all these threads would be able to run in parallel. If multiple threads enter or try to access single bucket, then in that case, only one of the threads will succeed first and will be able to insert the value in the bucket. The other threads will wait until the first thread releases the lock. Then a second thread will get the lock and perform the operation on the same linked list or the same bucket. Okay. So the key thing here is that hash table is a little more parallel than linked lists, because in hash table we have multiple linked lists, and here we have 101 linked lists, okay, which means at most 101 threads can perform operations on this hash table simultaneously or concurrently, okay, without any fear of corrupting each other's data. That depends on the values that they are manipulating, because the bucket is calculated based on the value. Okay. It is possible that all these threads may access different buckets. It is possible that all these threads may access same linked list, because it might happen that those different values being used by those threads are again all mapping to the same bucket. Okay, if we are mapping to the same bucket, then the bucket will become a bottleneck, and the threads will be accessing the bucket or linked list one after each other in a mutually exclusive manner. But if the values are mapping to different buckets, then all these operations can be performed in parallel. So here is the scalability of a simple linked list and a hash table. Okay? A linked list is here by circles, where in linked list, the way we have implemented it, only one thread can access the linked list at any given time. So as the number of operations increases, the execution time also increases. But compare that to a hash table, where it is possible for multiple operations to happen in parallel if they are operating on different buckets. So even when we increase the number of operations, the execution time does not increase. Okay? So this is a very scalable structure in its implementation compared to a linked list. Okay? So hash table is much more scalable than a linked list. That is because of the nature of the hash table, because linked list we have only one single linked list. In hash tables we have multiple buckets, and if the operations are being performed on multiple different buckets, then it is possible to do them in parallel. Okay? So it is much more scalable than a linked list. So these are some examples of how linked lists, queues, hash tables, etc., these different structures can be used among multiple threads in a thread safe manner. So I hope you understood the examples, and this gave you an idea that how you can use these structures as global variables being shared between multiple threads in a thread safe manner. And from these examples, you can at least have an idea and deduce that if you are given a new data structure, how you can share it among threads. Okay? So I'll stop the recording here. Thank you very much.